should be back.
You're from the computer. All right, yes, you're back. You're back.
Okay, this is off to an interesting start.
Look at the bad guys.
Okay, I think I might have solved the problem with this element.
Oh yeah. Hell yeah, brother. Yeah, let's go. I see me on your thing.
Okay.
Nice. Hello, hello.
All right. Okay, I think that means we might be good to, well, are you seeing, let's say, like, presentation and, like, some sort of, like, moving cursor? And
Yeah, I'm seeing your blue ball. I'm seeing your blue balls all over my screen.
that's exactly what I want. It's how I designed it.
Perfect.
All right. 1 second. Let's see. Okay. Well, actually, I'm, as you know, as we talked about, I made this in Canva. Okay, so I'm still learning the ins and outs of Canva. I guess I should have had it up like this.
Ooh, let's go.
And then apparently I can like move.
Fuck, let's go.
Did you hear that applause?
No, I didn't hear the applause.
There's an actual applause when you like remove the
country.
Oh, I think I might have this muted. Oh, I have it muted. It should be good now.
Okay, we're gonna go from the top. 1 second.
Oh wait. Okay, there we go.
All right.
All right.
Oh, that I also have this.
Oh shit! Ooh.
I literally just discovered that like right before going live.
That's awesome. Let's go.
Even though it's like whatever the most, yeah, it's interesting.
That is amazing. And before we introduce the class, and I'm sure many, if not everybody, knows who my prof is today, but can you introduce yourself to the rest of the class, Professor?
Absolutely. Well, it's not necessary to call me Professor, Mr. Professor, or however you, no, whatever you want.
Mr. Professor Campbell.
Mr. Dr. Professor.
Mr. Sir Dr. Professor.
And I need a pipe too. You're out professoring me. But yeah, I'm Corey Campbell. I'm a biochemist, and I cover science, research, and news, and biochemistry now on my stream. Although I haven't streamed in a bit, taking a break and preparing content like this, maybe a little more structured, hopefully interesting. Well, I have no doubt it'll be interesting because you're the interesting one here, and the entertaining
content.
one. And yeah, well. As we'll see, or hopefully we'll see, like this is a casual learning biochemistry. We're following a textbook. Let's say we'll be following a main one, and then I'm pulling from a bunch of stuff, and I'm trying to make original graphics. But again, my artistic abilities are much worse than yours. I have virtually no artistic creativity. But yeah, I'm going to try as best I can. As I mentioned to my chat before getting into the classroom, I intend for this presentation to be like the Constitution, a living document, where it's going to be, adapted and changed as we go. And I'll try to incorporate feedback, if something's unclear or something could be done better, or if everyone says that, this is crap and garbage and the animations suck and everything sucks, then I'll try to revamp things and make it better. And obviously, I prepared slides for I haven't prepared slides for an entire biochemistry textbook. I prepared 50, 60 slides that hopefully gives me enough time week to week to update it and have fresh content every time. To pretty much, we're going to be going from chapter 1 in a biochemistry textbook to I think the one that we're covering is up to chapter 35. Well, if in fact you want to stick it out that long, obviously. You can call it quits whenever you want and be like, this is the most boring stuff in the world. See you later.
No, this is gonna be great. I'm very excited about it. Make sure that you go fucking follow Corey Campbell. Corey Campbell's one of those people that I talk about when I say, "Hey, yo, you should be learning from people who know things to teach you, not just people on internet who sound authoritative." Fucking so make sure to go fucking check out Corey Campbell, based dude, fucking absolute mad lad. If you actually want to learn things from somebody who knows what they're talking about, make sure to go on over there. And I'm so excited to learn. I grew up in a cult, and I wasn't allowed a proper science education until I left that school in grade 9. So I'm excited to learn some science, and my background is very limited. So I hope to act as a, a way to help as well, to ask questions that chat may have and may feel like that might be a silly question to ask, but I don't know things, so like I'm gonna ask those questions myself. But if you have any questions too, make sure to put them in chat, and then we will do those things. And I am very excited to learn all the things that I was lied to about for so long.
I'll
So
try to keep
thank
the
you.
lies to a minimum, but I make no
Hell
promise.
yeah.
And yeah, obviously, you have free reign to ask any question at any time. Like, feel free to interrupt. And also, if through looking through your chat, you see a question that you want to ask on behalf of your chat, by all means, interrupt away. Where again, I want this to be a dynamic process, and not just me speaking at you and like actually, lecturing you like a parent.
Absolutely. And I do have one question from chat already, which I think is important, and I think helps also kind of set this up a bit on why it's important. As I said, I'm sorry, you said a cult? I was in a destructive high control group that was a young Earth creationist school. I was taught that the Earth was 6 to 10,000 years old, and that a lot of the things that scientists and everything that we're going to learn about here is essentially a lie. And it's all a myth. So this here is a way to learn the things that I wasn't taught, and to also help combat those things from continuing to spread, and being more knowledgeable myself, and help make everyone more knowledgeable thanks to the help of the amazing Sir Dr. Prof. Corey Campbell here. His Majesty,
Esquire.
the Honorable Esquire Campbell. So, yes, thank you again. So, yes.
And yeah, and I pretty much designed, at least what I have in mind is just, an hour each week. And if at any point you say that's too much and you want to cut it down to 45 minutes, like, feel free to say. Or if ever you want to extend it, by all means. So,
I do want to say just to that point, and then I'll let you just get in and I'll stop interrupting. For me, like an hour for me is like nothing. So like it'll never have to be shorter for me. So we're good to go.
all right. And so maybe a little bit of a warning too. Like, again, just as I'm ironing out technological kinks, and realizing that I cannot adjust the Discord window, otherwise it messes up the element on stream.
Mm-hmm.
And the current presentation that I've prepared, I've gone through it, okay, like probably 20 or 30 times now. So I'm hoping there's no mistakes, but unfortunately, I'm sorry, I am human, and there might be some mistake in there in terms of like a pop-up not popping up when in the order that I want it. But like, I got tired of like going through it and making sure everything is in order. But I'm sure we're gonna find something like, oh, this did not pop up at the right time, or this animation's not done correctly. But again, living document. The Supreme Court will amend it as necessary as we go. But yeah, we're gonna dive right into it. So my original my outline, okay, is I want this to be accessible. One of the reasons why I'm doing it is, well, one, to like get you involved because I like interacting with you, and two, to hopefully make things accessible. I'm all about making science accessible and open. And so I ideally what I have in mind is like, I'm gonna try and give like pretty much the background, okay, some chemistry and biology background, sort of like the minimum required that you need to know in order to we can do a deep dive or a deeper dive into biochemistry, to pretty much make it accessible ideally to virtually everyone on the planet, so to speak. Obviously, it gets greater than 5 years old or something. Hopefully, and I guess speaks English technically. Uh, but yeah, you got any questions before we go?
No questions quite yet, except for, do we have permission to take a pre-class TOS friendly dab?
Right before I take your attendance and I check it off that you are present in class, so now you're free to do as you wish.
Hell yeah, let's go. The fucking best professor. It's time for the fucking biochemistry TOS friendly dab. Fucking hey, I guess maybe one day down the road, I guess it's probably way too early to ask this and we're gonna learn things. But like maybe we can learn more about how and why like the dab breaks down and like how like the fucking nail gets hot and heats dab and dab turns to smoke and smoke gets inhaled and hail turns to high. That could be interesting things.
You will learn definitely about some of those things. Stick around long enough.
Shit, chat, you guys are so fucked. We're into some good shit, dude. Fucking, oh, goddamn. If any of us think that this is gonna stay just like a 1 hour fucking thing, I think we're all mistaking ourselves. Fucking, it's gonna have to be a little bit longer because this is gonna be fucking sick as shit. Cheers. All right. Thank you. Continue.
All right, let's dive right into it. And again, there might be some errors along the way. So, what is biochemistry as the starting point? Okay, now we can go with this official definition here, from the American Chemical Society. That's the real thing. It's legit. It's whatever the governing body of, American chemistry. And they say biochemistry explores chemical processes related to living organisms. It is a laboratory-based science combining biology and chemistry. No surprise, biochemistry is the combination of biology and chemistry. This is your, technical fancy jargon of what biochemistry is, but, what is it in a nutshell? At least to me, it's basically all aspects of chemistry associated with life. We're gonna be covering, chemical reactions. We're gonna be covering chemical structures. We're going to be covering some of the biochemical and biological changes that occur, in diseases and conditions. Cancer is a popular thing to cover in, biology, biochemistry, because, unfortunately, cancer is still a thing, as much as you try to research it. And so what I'm showing here, okay, on the right, this is a protein molecule, okay? And we're going to be talking a lot about proteins. Specifically, this is the protein hemoglobin. This is your oxygen carrier in blood, as in the oxygen that you breathe in through your lungs, okay? It ends up being bound by this hemoglobin molecule here. And it does, in my mind, a lot of cool things when oxygen binds hemoglobin. And hopefully, as you can maybe see, there's some intricate structure involved with hemoglobin. It's not just, this misshapen blob. There's maybe you can see some helices and other, fancy looping structures. Whereas we're going to be seeing a common theme as we go through, chemistry and biochemistry and biology, where overall structure is a critical and important theme. Where I'm going to be... Yeah, go ahead.
Oh, sorry. Is it too early to ask a question?
No, it's never too early to ask a question.
Fucking... chat asked this, and it is a good question. I was adding it to the list to ask later, but it did come up here. And maybe you'll answer it later. But what is life?
That is... That's a fantastic question. And maybe in maybe in about 12 slides, if we get to that, that will be covered.
Ooh,
absolutely.
All right. I'll hold my question until later. Okay, I'm paying attention. Hey, I ask soon. Fucking, it will be answered. Stick around. Thank you.
And what I would say is extra points to that chatter that asked that question, because that is a great question. That's why I included a specific slide to hopefully answer it. Because, we're talking about basically aspects of biology and chemistry. And it's like, well, biology, if I remember the translation from Latin or Greek, I think Greek, it's like, it's the study of life. Well, what is life? And that's a great both a great philosophical question and a great scientific question.
Oh yeah.
So hopefully we're going to be. I can't guarantee that I give you, the most satisfying answer, but I do have maybe some insight, or I try to answer it. But yeah,
Based.
fantastic question. And then, I think another follow up question is like, why care about biochemistry? Like, who cares? Okay. I'm a biochemist. That's definitely a bias of mine. Although I did my bachelor's degree in molecular biology, but then I pursued my PhD in biochemistry. But, I think it's cool. You might not think it's cool. I'm going to hopefully
I think it's cool.
try and make it cool. I'm going to hopefully try and make it interesting. But maybe, perhaps, to some people, most importantly, it has, major applications in human health and disease in terms of understanding disease processes. Generally, the overall approach is if we can really understand, okay, at like a molecular level, what's going on with disease and conditions, well, we can hopefully engineer or design therapies towards, what's going off the rails for some diseases and conditions. And I'm going to, as we go along, I'm going to try and incorporate research. And we're going to be doing, maybe as we get more and more progressive into the course, well, I'm going to try and cover more and more research and, bring it in. But just to maybe give you an example in terms of the applications of, biochemistry in human health and disease, we're going to touch upon very briefly, just a couple slides, this research here. So this is the title, okay, turning universal O into rare Bombay blood type. So what does that translate into? Well, for this research, as we're going to briefly see, they are altering blood groups, as in they're taking one blood group, okay, and turning it into another and actually making it accessible. Because in the title, this rare Bombay blood type is rare, and there's a problem with it that we get to right here in this next slide, okay? And you don't need to know all the details for this figure here, okay? This little blurb here, in terms of red blood cell antigens, play critical roles in blood transfusion since donor incompatibilities can be lethal. Recipients with the rare total deficiency in H antigen, the OH Bombay phenotype, can only be transfused with group OH blood to avoid serious transfusion reactions. So what does this mean, this, technical sciencey jargon? Ultimately, what it means is, so you have the blood groups here, okay? And I think most people, maybe not necessarily, but I think most people are aware of the typical blood groups, okay? The O, the universal donor, the A blood group, the B blood group, and the AB blood group. But then there's this actual rare one that, since the way it is, pretty much you don't need to be concerned with the jargon of the legend up the top. I would say pay attention to the...
I have a question about this after as well.
Yeah, absolutely. Pay attention to, the shapes, the triangles, the squares, the circles, the blue squares, where the O blood group, okay, since it's just a triangle, a circle, and a square, well, that means it doesn't produce a reaction when given to the A, the B, and the AB blood groups, okay? But this rare one, this Bombay blood group, okay, since it is just a circle and a square, okay, well, individuals with this blood type, okay, they can only receive blood transfusions from someone who exactly matches, basically. Think of it sort of as like organ donation. Like they need to be really, essentially in this case, perfectly matched. Of if you have this rare blood group, okay, then you can only receive blood transfusions from this other who has the exact same rare blood group. Hopefully you can see the issue of well, if you're rare and you're relying on someone else with the rare blood group to get a transfusion,
that's going to be an issue.
That's going to be an issue. Okay,
Math don't math good.
Exactly. So
unless you all just become blood banks until you're unhealthy and then you just share blood. But then that's not much of a life. That's just you're just spitting blood around.
And, well, there's definitely research trying to make, essentially, artificial blood. And maybe we'll cover it at some point.
Yo, fucking... and I think that this goes in with the question from chat, too. But, so would their blood be, worth, a lot to a blood bank? Would they be oh, you got O, beta, or B, fucking beta. You got Bombay blood group? Like, we'll give you like fucking like $1,000 a milliliter on that bad boy. Like, is it worth more? Like,
I don't know if blood banks like pay for blood, but let's say
sure.
with the right person, if you happen to come across a wealthy person that has that rare blood type, and they're looking for a transfusion, they almost certainly would be willing to pay a pretty penny
Yeah.
to get it.
Yeah.
So the ultimate goal of this research is like, well, is there something we can do to basically make more of this rare Bombay blood group? Now,
Before we move on, I do want to make clear that I am for blood communism and I'm not for fucking, profiteering off the sale of your blood. I want to make that clear. I was just wondering if it happened. Continue.
I second that statement as well. Uh, Now, let's say the question is, okay, between the O blood group and the Bombay blood group, pretty much the last two on the left, do you see any, overlap
Yo,
or any differences?
did you pick this because you have to just make sure that it doesn't give its fuck? Is that why you picked this?
Yeah,
Oh my
absolutely.
god, that is so good. Oh fuck! If you get rid of its fuck, the triangle, then it becomes O.
Exactly. So, okay,
Oh my god, that's so funny.
that's
What does the
essential.
fuck stand for? I'm sorry. There's
No,
no way
no,
that actually stands for fuck. Is that what you call it, a fuck?
yeah, you're not wrong. Yeah, there's reasons for this. We're gonna find out why they name it. Let's say there there's a rationale behind it in terms of what it's doing, but it's also coincidentally like scientists do have a sense of humor, believe it or not, where we do try to especially geneticists have really great senses of humor in terms of if you discover a gene and you choose scientists, geneticists come up with all kinds of wild names for genes, but yeah, so
Okay, sorry.
basically, okay, they're trying to get rid of the red triangle. Okay, so just as maybe a little bit of review and a preview in terms of what we're going to be trying to get a better understanding of. So, yeah, I highlight this Bombay rare blood group. So,
Before we go on, can we go back for a second?
absolutely.
Okay, so Bombay is obviously like the rarest, but then does it still get like varying levels of rare? Because in school I was taught, and I got like a couple of questions. One is, are there more rare blood groups? Second is AB the second rarest, if you don't include Bombay the rarest. And could you tell Jesus's blood type?
Ooh. In terms of the I
So
can't say with any confidence in terms of like I know O is fairly rare in terms of universal donor. Obviously, as they say, this ultra rare Bombay blood group is ultra rare. For the other ones, the AB and the combined AB, I can't remember the frequency. Like I know I've covered this before. Like I've seen tables in terms of frequency. It's just like yeah, I've heard that type of information is like sort of in the deep filing cabinet of my brain.
because I was told in school that fucking this is when I was in my Catholic school after I escaped the young earth creationists, and they were like weirder in different ways. They made different claims that were a little different, but the claim was that Jesus had AB blood type and it's the rarest blood type.
Oh
Which
well, that's
and that
definitely
has
not true.
okay, yeah, well, that's what I was taught. So like that's why I was thinking like, okay, assuming they didn't know about Bombay blood, would it then be the second rarest?
I'm
And then
I'm
like
pretty
how
sure AB is not like super. I could be wrong. Like again, I haven't. That information's a little bit deep in my brain. But I'm pretty sure AB, the combined AB blood group, is really not that rare. I don't think it's like ultra common, but I'm pretty sure it's not that rare.
And would you be able to tell someone's blood type from 2,000 years ago?
It's a really good.
Even if you had his bones and shit, which they fucking don't. The
Would the
claim is based on the Shroud of Turin, just so you have a little bit of
Yeah,
background
that
knowledge.
I definitely heard of. With the right, technically, I guess with the right preservation, sort of like a Jurassic Park type of thing, of like
The
this,
cotton amber.
yeah, the cotton amber somehow.
What if we
As a-
found Jesus cotton amber? Oh my god. Is that possible? No, he's way too young to be like, unless they threw him in like an amber mine. But is that even a thing that exists? Is an amber mine a thing, or is that just like honey over time or some shit?
Yeah, no, I don't think it's really that much of, at least not to that extent to like to encase an entire body. I could be wrong. Definitely not an
Yeah.
expert in amber, but that seems outside. That seems like way too much amber to cover an entire body, all coming from like a tree or something. So
That's
yeah,
fair.
pretty much they just want to get rid of this red triangle, okay, or they want to get rid of the fuck, so to speak. So all I'm pretty much highlighting here is the blood groups, okay? But also, okay, we don't need to really be concerned with this figure here. I just want to show it, again, as a preview of, like, this is some of the stuff that we're going to try to be, providing an understanding to be able to, like, look at figures like these and say, well, what's going on here, okay? Where pretty much you just need to be aware, like, instead of, like, triangles, circles, and squares, like, this is what the actual molecular structures of the blood groups look
Oh
like.
shit. Okay, the circles and the squares were way chiller.
Yeah, exactly. Where
God.
understandably, even for myself, when I first learned this, it looks intimidating looking at these molecular structures and all that stuff, and it definitely at least took time for my brain to adjust to look at these structures and understand them, and that's why we use shapes like triangles, circles, and squares. But all that to say is like this is what at the molecular level what the blood groups look like. Your O blood group, your A blood group, and your B blood group, and obviously your AB blood group with the combined both. So, what did these researchers try to do? Or what did they actually do? Okay, well, yes. So they took the universal O blood group, okay, they want to start with that, and they want to go to the Bombay blood group, the ultra rare one. That's their beginning point, that's their end point, okay? And what they did, okay, this is a description of what they did, okay? We discover, okay, fuck OB, from the mucin degrading bacteria, blah, 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 fancy whatever Latin name, as an alpha-1,2 fucosidase able to blah, 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 carry out a chemical reaction. A bunch of technical scientific jargon. So this is the reason why, okay, to answer one of the questions, of like, why did they name it FUC? Fuck, because...
Fucicide.
Because as a result of that, as in what it does, okay, so in, let's say, less technical terms, okay, they took this enzyme, okay, fuck OB, and what it does is it pretty much, it gets rid of what they call a fucose group, the red triangle, okay, and that's why I've, that's what they removed, where that's what that enzyme does, okay, that enzyme protein, from this organism, okay, it just removes that red triangle. That red triangle is actually a fucose, okay, it's a sugar called fucose, so it removes a sugar group from the O blood group, and that turns it into, okay, the Bombay, the ultra rare Bombay blood group.
Okay, sorry, maybe you said it, but how do you get fuck OB? How do you fuck OB here?
The OB is, I don't know for sure, because it's been a minute since I read the paper, but I believe... Yeah, go ahead.
Oh, sorry, I'm just like rereading it. They took an enzyme protein called fuck OB, so they like made this thing, or this is like a thing that just exists? Like, did they make
exactly.
this, or
so
they just figured it out?
This is a thing. Great question. Yeah. So this exists as in they're pretty much they are exploiting nature, as in bacteria. Okay. This fancy Latin name here, Akkermansia mucinophilia. Okay, that's a bacteria. This bacteria happens to have this enzyme protein called FuckOB. Okay.
Oh yeah.
And so what they did is, well, they found this in nature, and this is going to be, actually, this is a great question, because this is a common theme that we're going to be encountering over and over, of, like, finding things in nature and exploiting them or using them for our own purposes or towards our end, or to engineer them, to make them better, or to apply them for human applications. So this is in the case of, like, we found something in bacteria, okay, and now we are going to hijack it for our own purposes. We see that it carries out this reaction of removing, conveniently, the red triangle from the O blood group, that then turns it into the Bombay blood group. And that red triangle, okay, in chemical terms, we call it fucose. That's just a fancier word for a certain type of sugar or carbohydrate. So that's in a nutshell.
Glucose,
What?
not to be confused with fructose,
So
also a type of sugar, or is that
exact.
the same thing?
No, no. So you're right. It's exactly a sugar as well, as in a lot of sugars like fructose, as you said, glucose, and in this case, fucose. They end in OSE. That's
And
a
sucrose, is that a thing, or am I
yeah.
making that up?
No, you're not making that up. A sucrose is a combination of both glucose and fructose mashed together, basically.
Let's go. Fuck.
So,
Okay.
generally speaking, let's say in chemistry or biology, if something ends in OSE, you can be pretty confident that it's a sugar, or related to a sugar. Where we try to be a little bit rational in our naming things. So yeah, this is in my mind a really good application and proof of principle of the power of biochemistry of pretty much literally changing a blood group. And there's other similar research. Pretty much instead of turning the universal O blood group into this ultra rare Bombay blood group, there's other research showing, but it's a little more complicated, of turning
Bombay
going
into-
back, turning AB and AB into the universal. As in, since O is the universal, if we can generate unlimited supply of universal blood group, well, then we've solved a lot of our blood supply issues. But the research there is a little bit more complicated. Because, yeah.
Can you? Oh, can
Yeah.
you? No, never mind. That's what you're doing anyway. Sorry, I'm dumb. Oh no, sorry. Can you just give it a fuck and turn it into O, instead of taking the fuck away and turning it into Bombay? I guess that would make them pointless because they can't fucking work on O, dumbass.
So you're actually asking a really great question. As in, you're asking, can you go in reverse?
Yeah.
Right? So technically, a lot of enzymes, okay, can go in reverse. As in, hypothetically, okay, it should be
I can
possible.
put that thing down, flip it, and reverse it.
Exactly. Hypothetically, it should be possible. Just as you can remove, okay, the fuck, you can add fuck as well.
Oh, fuck. Yeah, you can give a fuck. Okay, cool.
Exactly. The only issue is, like, if you're starting with the rare, okay, well, if you're starting with the ultra rare Bombay, okay, your supply is going to be limited. And like, that would be great if we had an unlimited supply of Bombay, and then we could just turn it into the universal O. But yeah, hypothetically speaking, you could absolutely add in the triangle and go in the opposite direction. So that was actually a really fantastic question. So that's why I encourage you to. There's no bad question here in my mind.
Nice. I had a buddy who had an endless supply of Bombay, and then it turned out not to be enough, and he developed a blow problem.
That sounds about right. So,
Yeah.
we're going to be talking a lot about enzymes, okay? And the power of enzymes and what they do and all that stuff, because they do really cool things. And enzymes tend to be proteins. And so we're also going to be talking a lot about proteins and all that stuff. So basically, most enzymes are proteins, but not every protein is an enzyme. And we'll clarify that as we go. So, that's why I think you should care about biochemistry. Okay, hopefully I've made a case for it, but even then, if you're still on the fence, I don't blame you. But that's the best case that I got so far, without getting into the nitty-gritty details of other research. So, with that, I'm gonna, again, try to lay some sort of foundation, some chemistry foundation, and some biology foundation, so that we can now dive into biochemistry. So what is some of the chemistry that you need to know? Okay, so a very quick, chemistry 101. Obviously, you can't avoid the periodic table of elements, okay?
Let's go.
You have all these elements here, okay? Looks super complicated, looks, understandably intimidating, okay? Even to myself, because sure, I'm a biochemist, but even I myself, there's a reason why, I pursued biochemistry and not hardcore chemistry, because I actually don't really care about most of the elements from the periodic table. And conveniently enough, okay, or coincidentally enough, okay, biology and biochemistry, we pretty much can ignore the vast majority of the periodic table, okay?
Let's go!
What are we really concerned with?
Majority.
Okay, we're concerned with carbon, okay? Carbon right there, the sixth element from the periodic table. We're interested in nitrogen, okay? The seventh element of the periodic table. And then we're interested in oxygen there, the eighth element on the periodic table. Okay, and then lastly, okay, one of a key player as well is hydrogen. Okay,
Mm.
number one.
Would
And I
you?
would, yeah, go ahead.
Oh, sorry. Oh, sorry. Oh, I was just gonna say, would you say that they're like kind of like the working class of the elements, and then the rest are kind of just leeches off their work and just get too much credit?
Yeah, yeah, like they are absolutely the foundation of pretty much all life on Earth. Absolutely, yes.
Hell yeah.
And
Or-
this table here, okay, is pretty much like the distribution of the elements, okay, in the human body. And hopefully you can see that, greater than 95% is just oxygen, carbon, hydrogen, and nitrogen. Okay, and I would say it's not critical for you to, know this for biochemistry, but I just for the sake of knowledge, okay, recognize that the periodic table is organized by number of protons, okay? As in hydrogen number one, that means it has one proton, okay? And then helium number two, that means it has two protons, okay? I'm consistently surprised at how many people that I know, even at an advanced level of chemistry, don't seem to remember or recall that the periodic table is organized by number of protons. But yeah,
If you were to organize a periodic table, how would you do it?
to be perfectly frank, like this is the best that I know of to organize it, as in it makes sense and it's nicely laid out and things are, I would say, pretty well categorized. But I'm not a chemist, so I'm definitely not the world-renowned expert in the periodic table. But like, yeah, it's a nice, convenient way to organize it, and it makes intuitive sense because as we're going to see, okay, one of the reasons why it's organized by number of protons, okay, is because the protons, as we're going to, well, we might just, it's probably a good transition into the next slide, where, yeah, as a highlight there, pretty much we're largely concerned, the vast majority of the time we're going to be dealing with pretty much four elements: carbon, nitrogen, oxygen, and hydrogen. So we can ignore pretty much, greater than 90% of the periodic table. And so, one of the reasons why, okay, it's organized by number of protons in the periodic table is because, so here, as I'm showing, is your very simplified model of the atom, okay? You have your protons and neutrons in the nucleus, okay? Your red spheres here and your blue spheres here. So the protons are in the nucleus, okay, forming, the core and making up the majority of, the mass of the atom. And so we organize it, or I assume those who made the periodic table, all the experts there, they organized it by number of protons because, like, they're in the core and the core is not really changing except for, neutrons, as I cover here. But number of protons is not really changing. They're kind of like stuck there and they're pretty constant. And as we're going to see, okay, number of electrons will change. As I'm showing here, number of neutrons will change. So if electrons are changing and if neutrons are changing, then it becomes really difficult to organize the periodic table if we organize it by electrons, because as we're going to see, electrons are moving around a lot, being transferred. Electrons are, promiscuous, so to speak. And so if we start organizing the periodic table by electrons, it gets really messy, because then things just get jumbled. So I assume they've organized it by number of protons because they're at the core, they don't really change, they're in the nucleus. And the only difference is, yeah, go ahead.
So I have two questions. One's kind of just like more just like I'm interested to know, and the other one actually has to do with this. First of all, if it was organized by the coolest, what are your top three of the coolest elements? And what is an isotope? Did you explain that and I missed that? Or
No, I have not
I don't
explained it.
Okay.
Yeah.
Okay.
The coolest, well, as we're going to hopefully learn and appreciate, okay, carbon is really cool. There's a reason why I also singled out carbon here in my example of, like, neutrons, just because, like, yeah.
666.
Well, yeah, there's that too. But also, like, we are carbon-based life forms, because carbon, as we're hopefully going to see, has, really special properties that make it, stand out in the periodic table. And why,
I think I see those properties.
why we are carbon-based, yeah, satanic properties, one might say.
Yeah, it sold their soul. I see it right there. 666.
But yeah, so another thing this is not super critical, to understand biochemistry, but it's good to know that they exist, and most people have at least heard the term isotopes, okay? So, like, what does that mean? What are isotopes? Well,
Yeah.
basically, that's where your number of neutrons are changing in the nucleus of the atom, okay? So pretty much, so carbon 12 that I've shown here on the left, that's what you find in nature. That's what you find most frequently in nature. That's
And that's what
your
they're carbon testing for, and that I was taught is a lie and doesn't do anything, right? You're carbon testing for C12 carbon, or I
if
guess
I
there's different types. I guess.
well, there's different isotopes. I can't remember it might be carbon 13. It might actually be carbon 13. I can't remember offhand.
Okay.
But ultimately they are, when it comes to like carbon dating, like it's
Yeah.
some sort of isotope like testing, absolutely. And isotopes, okay, pretty much. So that's why, okay, we call it still carbon, okay, even though the number of neutrons change, okay, it's still carbon. And we're going to see that the number of electrons, okay, can change with carbon, okay. In fact, it's actually a good thing that the electrons change with carbon, because that's what gives it some special properties. And so that's why, okay, we organize, or not we, other smarter people than I organize the periodic table by number of protons, because, if the number of neutrons, okay, resulted in a different element, well then, again, it'd just be really hard to organize, because, you have carbon 12, you have carbon 13, you have carbon 11, and we just have to come up with, new element names. Like, well, this is not carbon anymore, it's something else. But no, it's still carbon. It's just carbon 13, with a different number of neutrons. So yeah, go ahead.
Because it's okay. I'm dumb. I misinterpreted neutrons for protons. Okay, never mind. I was gonna say, if it changes, then how is it not a different thing? But that's because it's by proton. Okay.
Yeah, exactly. No, you're absolutely not stupid. Not at all.
So protons cannot change, or can they? Can you turn a motherfucker into another motherfucker by like knock fucking a proton? I know that's probably way too far ahead of where we are, but like,
No.
is that shit you can do?
Well, so that's where, okay. I'm not a nuclear physicist, or an atomic physicist, but hypothetically, you should be able to change the number of protons, or maybe some protons in an atom, but that's where you're actually changing sort of like the physical nature of like, if you take this carbon 12 here, okay, and you knock out a proton, okay, where it's now 5 protons, that makes it no longer carbon, okay,
Yeah,
by our definition.
Does it make it the whatever one is 5?
Yeah, exactly. So we go back to the periodic table. Exactly. So that would make it boron.
Boron? No way. So like that legitimately like turns that fucker into boron. So like, are you saying like in a similar way to like the Bombay and the O blood, like you could just fuck some shit over and change fucking regular ass fucking shit into like super rare smart guy shit if it happens to be near one?
Well, so let's say hypothetically, everything you said is like, I guess hypothetically potential. Let's say the difference is, I assume, I'm not a nuclear physicist, but I assume it's probably way more difficult to change the number of protons in an atom, as opposed to we happen to found a protein or enzyme in nature that happens to remove triangles from a blood group. There's a lot of that lying around, as opposed to it should be possible. It's a great question. It should be possible to knock off a proton from an element, but that would actually change pretty much like the ultimate, like, physical nature of that element, and it's no longer that element, as in
chat saying that's alchemy at that point.
Maybe. Well, yeah, that's what Newton tried to dabbled in a little bit of alchemy, if I remember correctly. Where so going, if you added a proton to carbon, okay, well, you're actually now changes it into nitrogen. Okay, you're pretty much like changing the actual physical nature of the thing, and that's why we've organized it by number of protons. So like pretty much the number of protons gives its essence, gives its soul, I guess, so to speak.
So like you couldn't remove a proton from gold to make it platinum, or add a proton to platinum and make it gold.
That I don't think is possible at that level because, like, yeah, otherwise you can have an unlimited supply hypothetically of like gold or whatever. Pick your element.
Yeah.
Where it's probably feasible for some elements to like knock off maybe like helium or something. I don't know.
Yeah, it doesn't take as much
I'm totally
energy.
pulling things at this point out of my ass.
Yeah, fair, fair,
But I think in theory it should hypothetically be possible to do that. But
fair.
I think as you get to like yeah the other whatever fancier elements, not quite so easy.
Yeah.
So yeah, that's ultimately again not super critical for our purposes, but just for your information. Like that's what that's what isotopes are. It's just you are now changing the number of neutrons, and why we call it carbon 12. Okay, so it's because if you add up 6 protons and 6 neutrons, you get 12. And why we call it carbon 13 because if you add up 6 protons and 7 neutrons, you get 13. And so that's pretty much what it is.
So carbon 12 is just regular fucking carbon. That's just some rag shit because
Yep.
it's on that 666 gang.
Exactly. It's the
Hell
satanic
yeah.
carbon, and we're actually going to be dealing with the satanic. We're largely dealing with the satanic carbon as we go through.
Oh, that's
biochemistry.
my boy. That's my boy. I feel like a deep spiritual bond and connection already with carbon 666. Will it be a covalent bond? What is that? I don't
Ooh,
know. Maybe we'll
oh,
learn about that.
yeah.
I don't know.
You're ahead of the game. Actually, you're
I only
almost.
know that about from 21 Jump Street. That's how I know about that word.
But a thing to keep in mind is like this is the simplified model of the ad. Like there are multiple. There's a quantum model, all that stuff. This is just like a pretty picture. But like to
Yeah.
illustrate the point that you have your core of the nucleus, your protons and neutrons, and like yeah, you have your electrons in orbit. But they're not like in orbit like planets of like they have this like perfectly defined orbit. Like no, they're kind of like well moving around all over the place. You can kind of think of them as electron clouds is a term we often use of like they're floating around in semi-random motion, all that stuff. But this is just like a nice way to sort of like I think to think about it. And it's like yeah, they're orbiting around, and yeah, electrons are going to be going all over the place as we're going to be seeing.
Before we move on,
Mm-hmm.
would you say that there is truth in the saying or the quote from Nacho Libre that I put a lot of stake into? That beneath the clothes you find a man, and beneath the man you find his nucleus. Would you
Uh,
say that that is correct?
that gets my seal of approval. Absolutely, I cannot dispute that at all whatsoever.
Mm, mm, mm. Wow. Science is truly amazing. It can make you appreciate blood, the tiniest aspects of life, and the timeless words of Nacho Libre.
Absolutely. So as I think you were like again ahead of the game because like you asked a question, I think you alluded to covalent bonds, okay, and we're gonna be getting to that shortly. Of like so, you've briefly covered some fundamentals of atoms and the periodic table. Okay, well atoms like interact with each other. Okay, and so how do atoms bond with each other? Okay, a little again chemistry 101. So there's a little bit of a guiding principle here of
Sure.
atoms very often want to fulfill the octet rule. Okay, so I have two elements here. Okay, sodium and chlorine. Okay, from the periodic table.
Oh shit.
Okay, and okay, there's many electrons here. Okay, where in the case of sodium, you count them up. Okay, you have we can do this in real time in terms of you have 4, 6, 8, 10, 11. You have 11 electrons, but
Shit.
hopefully you can see that they're in little orbits there.
Little spinners.
Yes, they're in what we call shells, so to speak, in some manner of speaking.
Yeah.
Now, what matters the most, okay, are the outer shell electrons. We call them, fancy terminology, valence electrons, the ones on the outside.
Ooh.
Okay,
What is considered outside? The
that's
farthest most one? Or
exactly. So if you look at sodium, okay, so pretty much the one on the furthest outside, how many electrons do you see there?
one on the sodium?
Exactly. And then you have chlorine. Okay, chlorine
Two,
has
four, six,
17.
seven. 7 on the out. 7
Exactly.
valence, boys.
Exactly. You got
Uh,
7. And that's what I've
oh.
depicted here underneath. I've just singled out the valence electrons.
And are
Okay?
those kind of like their pawns that they can lose and like shit can go fuck off?
Yeah, exactly. As in what we call, as I've highlighted here, you have a
Uh,
full transfer of electrons. So, here is where my crappy animations come into play. Of like, okay,
oh shit,
sodium.
there goes.
Sodium gives, okay, an electron to chlorine. Again, another reason why we don't organize the periodic table by electrons, because like if it was by electrons, the sodium has now become a different element. So it's lost, okay? It's lost its valence electron. It's lost that
Oh
one outer one,
shit.
okay?
Fuck.
And so, but if you go back to the original picture, okay, if you just like get rid of the one on the outside, okay, how many electrons are in the new valence shell now?
There's nothing. Oh, the new valence cell is 2, 4, 6, 8.
Yes, exactly, 8, as in
Oh
that's
shit.
that's how they are fulfilling that octet rule, as in this case, okay, they want to get to 8 outer electrons, okay? And it's easier for sodium to lose one, okay? And then it has a fully occupied shell. And then in the case of chlorine, okay, well, conveniently it has 7. This is why, they go together so nicely. And sodium chloride, that's table salt. That's what you put on food.
Yeah. Yeah.
And so, once the transfer of electrons occur, okay, in this second step here, you have sodium now, since it's lost an electron, okay, it's positively charged now, okay? It has a full positive charge. Since it's lost an electron, and electrons have negative charges. And then now chlorine, okay, since it's gained an electron, it's now negatively charged. It has a full negative charge, okay? And so you've had this full transfer of electrons. Sodium has given away one full electron to chlorine, and now you have a full positive charge, and you have a full negative charge on the chlorine. And so what ends up happening is, well, as most people know, opposites attract.
Yeah.
Where you get now sodium chloride coming together. And that is what your table salt is. 1 second, I gotta get rid of something in chat. Okay. So this is what we call an ionic bond. Okay? That's how you form an ionic bond, as in it's a full transfer of electrons. And they're transferring electrons here because in the case of sodium, if it gives up one, well, it ends up with 8 outer electrons in its shell.
Is it only considered full because now it's like 8 on 8 action? Is that why it's considered full?
Yeah, exactly.
8 on 8? Okay.
Exactly. As in now sodium has 8 and chlorine has 8. Sodium got to 8 by getting rid of something. Chlorine got to 8 by taking what sodium is putting on the table. And that's why they end up coming together to make table salt, or sodium chloride.
And do you want things to be like one to be positive, one to be negative? Like that's good, and like that's seen as like stable and happy and good.
When they come, when they come together like this, okay.
Well, they're
like
going to be attracted because they already splingle-dicked over it.
Exactly right. And so this is nice and stable. This is table salt. Okay, this is again what you put on your food, and it forms. Okay, I think most people have seen. Salt is like these crystals. Okay, it's solid, and and it tastes pretty decent. And so so as I mentioned here, it's ionic bonds are typically strong bonds. Okay, as in it takes quite a bit of energy to break the ionic bond.
More like fucking iconic bonds. God damn.
Exactly.
Dog.
That's another way to put it as well. So this is the fundamentals of an ionic bond. Pretty much the main message is, okay, you still want to fulfill the octet rule, okay? And this is one strategy that they are attempting to use to fulfill the octet rule of like transferring of electrons. Sodium gives up one, chlorine gains one, you get positive charge, you get negative charge, And when you have full positive and full negative, as in when you have a full charge, okay, you call them ions. Okay, that's why you call them ionic bond, where it's two ions coming together.
So like your battery that's a lithium ion is
Yeah.
like an ionically bonded lithium ass fuck.
It has a charge, exactly, as in a lithium. It has a charge, as in this sodium ion, full positive charge, the chlorine ion, full negative charge. They come together to form the ionic bond, as in two ions, full charges coming together.
So then would an ionic, would like a lithium ion be like one positively charged and one negatively charged lithium come fucking together? Or would it be like...
No, it would be lithium, lithium combined with like something like the lithium ion. That means that the lithium is charged. It's probably has lost an electron, as in it probably resembles something like sodium, as it has some sort of positive charge to it.
So it doesn't necessarily have to be combined with something to be an ion. It just needs to lose or gain an electron.
Great point of clarification and great question. So that's the thing of like you can have ions alone, and so when you add salt to water, okay, what happens to when you add salt to water? Does it stay as a crystal or does it disappear into the water?
Disappears into the water. That's why you use ISO with your salt when you clean your rigs.
As in the salt becomes dissolved in water, and in that scenario, okay, you have free sodium, as in it's no longer sodium chloride. It's like a bunch of sodium now alone like this, and a bunch of chlorine alone like that, floating around in water. We're gonna see similar to that. But the ionic bond, specifically the ionic bond, it's two ions coming together. So great question. Great point of you can have ions alone, a sodium ion. You can have a chlorine ion alone, okay? But when they come together, that's when they form the ionic bond here, in this case. Absolutely.
Okay. If you put enough salt in water, could you get enough chlorine to, like, poison someone?
Well, so...
I'm sure that water would taste so bad at that point.
Well, what can happen is you can add so much salt to water that, like, it no longer dissolves, and you'll be adding...
just get sludge.
Yeah, exactly.
Yeah.
And this, and actually what you mentioned, so this also highlights, let's say, an important principle of, like, so chlorine, okay, like chlorine gas, okay, chlorine's toxic. Okay, or let's say chlorine gas is toxic, but okay, the chlorine ion here, okay, that's in your sodium chloride, well, that's not toxic unless, I don't know, you're eating, kilograms or pounds of it. But like, no, the chlorine in one form, chlorine gas, okay, that's toxic, but chlorine in this form as an ion in sodium chloride, that's not toxic. Okay, you can consume that in reasonable amounts with like no negative effects whatsoever. So
chlorine in your pool, probably shouldn't drink.
Yeah, although you can still, like, probably not recommend it.
You can get a little bit of pool water, but you shouldn't drink just a straight chlorine.
Exactly. So, and this is
same with Dasani water. Chat did comment that is what Dasani water is just like the worst fucking just saturated water of shit. Yes.
Yeah, I wouldn't
shouldn't drink that either.
So those are the fundamentals of an ionic bond. So... yeah, is that, let's say, hopefully clear, unclear, even more confusing than ever?
Yeah, no, actually, that actually kind of makes sense. That definitely makes sense. That fucking buddies just spin fucking around, having a time. Fucking chat did have some questions that I wanted to see if we can get some, like, clarity on. Essentially saying, like, where was it? I don't know if it was really a question or more of a statement that, like, the less electrons on, like, valence electrons, the more, like, ability to move around. I hope I'm not saying that wrong.
Yeah.
More freedom. I was probably saying that wrong. I forget where I read that.
Yeah, you can go.
Oh, yeah, the fewer outer electrons, the more space they have to interact, was the proper wording.
Yeah, if that's a statement, that sounds about right in terms of, overall, like, sentiment. Yeah.
And then, so they said, oh, sorry. And then there's a question after that.
Yeah, go for it.
So less electricity / friction. Like, I'm assuming, like, when you're talking about, like, them losing it, like...
well, so, like, there's one of the reasons why we call them ions, and electrons are obviously involved here, where it's like, yeah, so, well, without getting into the nitty gritty of electricity, but like, yeah, electricity, like, that is the flow of electrons, okay? That's why, so, and this is why, okay, so, this is also good proof of principle of like, okay, you have, well, presumably you have tap water, okay? Just as I have tap water, okay? But, you know, strictly speaking, okay, what's coming out of your tap, like, it's not water, okay? It's not pure H2O, okay?
They're putting chemicals in the water. It's turning the freaking frogs gay.
But, you know, the water that, let's say, I use in the lab, or have used in the lab, you know, the distilled water, the ultra-pure water, okay? That has pretty much, like, the vast majority of the stuff, okay? Like, the ions, like, you know, the chlorine, the calcium, pretty much it should be as close to as possible,
H2O.
like pure H2O. And that doesn't conduct any electricity, okay? As in, like, if pure H2O, okay, if you drop your toaster, your plugged-in toaster into, you know, while you're standing in it, do not try at home at all, just saying, hypothetically speaking.
Try it.
If you have access to, you know, ultra pure, okay, actual pure H2O, okay, and you drop your toaster in it, okay, there will be no conductance of electricity. But if you actually use tap water that has things like sodium, okay, and chloride and calcium, yeah, exactly, has ions dissolved in it. Well, ions have, as we've seen, they have electrons, okay, they have electrons that can move around, okay, and therefore, okay, your tap water can conduct electricity pretty well. So that's well, that's, let's say, the crude way of describing electricity. 1 second.
Chat said that a student one time brought pure deionized water to our chemistry course potluck, and the chemistry professor laughed so hard.
Yeah, well, so it's generally not recommended.
It tastes like shit.
Nah, it's not generally recommended to drink, you know, ultra pure deionized water. But
is that because it like attracts shit like that, like your body needs, and like fucks it out, or what?
Well, this goes into a good principle of biochemistry. As we briefly touched upon, okay, ultra pure, you know, distilled water, deionized water. It doesn't have the ions like sodium, chlorine, and calcium dissolved in it.
Electrolytes and shit.
Exactly, it doesn't have the electrolytes in it. And so what tends to happen is it's in the reverse direction. It's pretty much ultimately the same reason why, you know, you're not supposed to drink ocean water, okay? Because the salt concentration is so high that pretty much in order for your body to get rid of, if you drink seawater, your body has to pretty much dilute it.
Water.
Yes, it has to lose more water to get rid of it, okay? It's the same principle, but in reverse. Of like, well, if you're drinking, okay, water that has no electrolytes whatsoever, well, your body has to add in its own electrolytes to, like, pee it out, basically, or get rid of it. And so, in a way, you're just, like, leaching stuff away from your own body. And so that's why it's generally not recommended, although, like, in reality, like, drinking tiny quantities, it's not actually, like, poisonous or whatnot, but, like, yeah, you should definitely not be drinking gallons and gallons of this stuff. But, you know, at your own risk.
Damn. I was going to go get some, but I guess not.
So those are the fundamentals of an ionic bond. So, I think you mentioned this earlier of a covalent bond, okay?
Oh, let's go.
Now we're going to cover the fundamentals of a covalent bond. A very brief primer on covalent bonds. So this is another way, okay, this is another strategy that atoms use to fulfill that octet rule, okay? Instead of transferring electrons, okay, we can share electrons, where electrons have, you know, some commie tendencies.
Let's
like
go!
Sharing.
Comrade covalence!
Exactly. So, I've used this example of, okay, carbon, okay, nice example. So how many electrons does it have in its outer shell?
The carbon? It has 4.
Exactly, it has 4, which I've depicted here. Okay, and the hydrogen.
Oh, yo, it just clicked in my mind. I don't mean to cut you off, but this
That's okay.
might help someone else because this just clicked in my mind. The outer ring fuckers are called valent, right?
Yeah,
And
valence
these
electron.
are covalent.
Yes.
Like they're like together.
Yeah, yeah,
That makes sense just in its very name.
exactly. That's the rationale behind the name.
Oh
We
shit.
try to be sensible of like, yeah, it's
Fucking sensible
we're gonna
biochemists.
we're
Chemistry
going to share atoms together, share outer valence electron together.
Let's go. Let's
So,
go.
so here is where hydrogen. Okay, hydrogen, as you can hopefully see, it only has one electron. Since it's number one in the periodic table, it has one proton and one electron. Now here is where, okay, hydrogen is its outer shell is a little bit different. Okay, where its outer shell, it still wants to get a full shell. Okay, but the version of a full shell for hydrogen is just 2 electrons. Okay, we're going to see that step by step of like that is effectively okay what happens. Okay, where again don't you don't need to dissect it too heavily, but if you
Sorry.
count, yeah, go ahead.
What is it that limits it to 2, and how do we know how much it's limited by?
Yeah, so that's an excellent question. So let's go back to the periodic table. Well, actually, no. I have a future slide. I did actually think of this as a question.
It's okay if you say we'll answer it later. That's fine.
Yeah, it's
You
actually
can answer it later.
Should be in
Yeah,
about
you don't have to go
two
to it
slides.
now if you don't want to. Okay, cool. Okay.
Yeah, because that is a fantastic question of like why is hydrogen behaving so weirdly? Because it's totally a valid question and is counterintuitive based off of everything that I've said so far. Okay. But so now, okay, if you add up, okay, all of the atoms, okay, here's where the sharing occurs. Like you have your original 4 valence electrons from carbon, okay, but now you have this bond here, okay, where pretty much now carbon and hydrogen, they're sharing together. So this picture here kind of like, crudely represents it. Like now they're overlapping, where if you add up now all together, 2, 4, 6, and 8, okay, now carbon has 8 electrons in its outer shell through sharing with hydrogen. As hydrogen is, sharing its electron, saying, hey, you can spend some time with my electron, and, it can spend some time in your outer shell. Basically, you can have a sleepover with my electron, and to fulfill your outer shell to now get to 8. And you make this this molecule here called methane. Okay, so these are 1, 2, 3, 4 covalent bonds. Okay, and as highlighted here, covalent bonds are generally strong. Okay, pretty much ionic bonds and covalent bonds are in your category of very strong bonds. Okay, and we're going to see
Which one's stronger? All right. Does it depend?
That's an excellent question. On average, okay, if I remember correctly, ionic bonds are generally stronger than covalent bonds because they're driven by full negative and full positive charges, and so it's pretty much like the ultimate attraction of like opposites attract, basically.
Yeah, they be fucking. They really do be fucking.
Exactly. And so in this case, probably ionic bonds would be like at the the top, although there might be some covalent bonds that might compete for it. But we're going to see, as I sort of put as a note here, okay, you have single, double, or triple bonds, and we're going to clarify that as we go. But what I've shown here, okay, in this case of methane, is you have 4 single bonds, as in 1, 2, 3, 4, as in 2 electrons make up 1 covalent bond. And that's what I've tried to depict with the
stick.
The yellow circles there. The stick with the yellow circle, the 2 electrons, that's 1 covalent bond, and then 3 more. But we're going to see that you can have double and triple covalent bonds.
Oh, let's go. Fucking. Yeah. You're not a real fucking commie bond unless you're getting doubled or tripled on the internet. Fucking, we got it. Let's go.
So these are your fundamentals of a covalent bond, where, as I highlighted, it's sharing of electrons. Okay, so ionic bonds, as a review, That's a full transfer of electrons. We're not sharing, we're like giving away or like donating, we're transferring. And then for covalent bonds, we are sharing, okay? We are commie atoms.
Let's go.
1 second. So those are your fundamentals of covalent and ionic bonds, okay? So now I think to answer the question, the great question that you posed earlier of like, why is hydrogen, okay, so strange? So just to like put it in a little bit of a perspective and some rules for covalent bonds, because as we're going to see, covalent bonds are going to be super important when it comes to biochemistry and biology. So I've highlighted, okay, our star players from the periodic table in the red boxes: hydrogen, carbon, nitrogen, and oxygen, okay? Now, as we just briefly went over, okay, carbon has 4 valence electrons, so 4 outer electrons. Nitrogen has 5, okay, and oxygen has 6, okay? Now, hydrogen here, hydrogen's is in a completely separate row, or using the technical term from the periodic table, it's in a totally different period, but that's just fancy term for it's in a different row. And the row, if you look at the row, well, there's only 2 of them in the row. There's hydrogen here, and there's helium here, okay? And so when you go from, this is where you have first shell, second shell, third shell. So that's why hydrogen, okay, behaves a little bit strangely, because its first shell, it only has 1 shell, and for that particular shell, it only needs 2 electrons, okay? But then if you're in a second shell, that's where you're in the 8, and same thing with the third shell, okay?
Where you're in 8?
Yeah,
not 3?
Sorry. Go ahead.
Oh, these guys here, sorry. I was thinking, so the first shell you can get 2, right?
Exactly. And
the second shell, why 8?
That's the
happen to be that.
That's the octet rule, where I've highlighted here. So carbon likes to form 4 bonds, okay? And how many outer electrons does carbon have?
4.
So what's 4 plus 4?
8.
Okay, now nitrogen has how many outer electrons?
2, 4, 7.
The outer ones, just the outer ones.
2, 4, 5, sorry.
That's okay, nothing to apologize for. So yeah, it has 5, okay? Now, nitrogen likes to form 3 bonds, okay? So what's 5 plus 3?
8.
Exactly.
But,
so pretty...
Okay, so that's, I guess, just, like, based on, like, the reason that it's 8 is just based on what has been observed that it likes to form as.
Exactly.
Not, like, that there's... Okay, it's just like, hey, this looks like this just happens to make 3s and 4s and 2s. It's not like... Okay, well, that makes sense.
Well, the ultimate answer is, like, it's energetically favorable, basically.
Yeah, okay.
Where it's like, without getting into, thermodynamics and all that, but like, yeah, this is energetically favorable to these atoms of like, for them
feel
to
nice.
Yeah, exactly. Where, makes them, feel pretty, and, super special.
Hell yeah. So then, sorry, just to kick it back 1 notch here. So then with lithium here, back when we were talking about lithium ions, so would that just need to lose a single electron, and then that would be positively charged lithium ion?
So that's where, again, there's a reason why I'm a biochemist and biologist. So lithium, that's why, like I said, I pretty much ignore the vast majority of the periodic table.
fair.
And so lithium, like totally lithium, like we encountered in nature, and like we dabble in it a little bit in biochemistry, but not really. But like, yeah, the fundamentals or like the unique chemistry of lithium, that's like that's outside my scope of practice, so to speak. But like, yeah, well, definitely lithium ions are a thing, and totally, I think lithium tends to be like, well, a lithium ion is positively charged, as in it has a tendency to lose electrons. That I know with a high degree of confidence. And that's why, as I highlighted here at the end, hydrogen likes to form 1 bond, okay, where through sharing, okay, through sharing with another atom, just one electron, it fills its outer shell with two. Okay, and with carbon, through sharing, as we going back to this one,
From
okay,
comrade bonds.
how many covalent bonds here are in this methane molecule? If you count out just like
Four.
this, exactly, there's four, because carbon likes to form four covalent bonds, because through sharing with another atom, in this case hydrogen, it gets to 8 electrons. Okay, and then that's why I've included nitrogen, where nitrogen, as you count it up, it has 5 in its outer shell. So it needs, through sharing, through forming 3 covalent bonds, 3 plus 5 is 8.
Yeah.
And then for oxygen, okay, 1 over, that has
6.
6, exactly. So oxygen likes to form 2 bonds, where if it's able to share with another atom and get through 2 covalent bonds, get 2 electrons, that gives it 8, and that's why oxygen likes to form 2 bonds. We're going to see oxygen double bonds quite often. We're going to pretty much virtually always see carbon with 4 bonds, and we'll frequently see nitrogen with 3 bonds, and hydrogen pretty much always with 1 bond. So those are your fundamentals for, the important atoms of the periodic table. Okay?
Let's go.
And so, okay, those are your fundamentals of like bonding and why, okay, atoms come together through ionic bonds and covalent bonds. So these are examples of intramolecular forces, as in they hold salt together, sodium chloride, okay, your salt crystals that you put on food. It's held together by that intramolecular force, an ionic bond. Okay, and just as as we saw the covalent bond in methane, it's held together by covalent bond, that intramolecular force. But in addition to intramolecular force, so I'm also highlighting here, this is a covalent bond between oxygen and hydrogen. This is a water molecule. We're going to be seeing that water is very important when it comes to life and biochemistry. But there are also intermolecular forces. Okay, as in not forces within molecules or compounds, but these are forces or interactions between 2 separate molecules. What do I mean by that? Well, I started with one water molecule, okay, and you have your covalent bond there. But what if now you have more than one water molecule? You have
shit.
2. This is... yeah, go ahead.
And that would be like a fucking water droplet. Obviously, there'd be more than just 2 fucking molecules.
Yeah,
but
yeah, go ahead.
Water droplets would be intermolecular, where it's just there's just a bunch of droplets together which make the bucket of water.
Yeah, and there's a reason why water forms droplets, as in, water has these special properties of it tends to be actually kind of sticky in terms of if you ever spill water on your table, it's not just one pass of the paper towel and all the water's gone. Typically it's 2 or 3, because water tends to stick to things, just as water tends to form these droplets that it looks like they have some sort of a surface to them. And that's
are you building some tension?
Exactly, surface tension, and that's going to largely be driven by these intermolecular forces that we're going to be briefly covering. So these intermolecular forces, okay, they're generally weak. There's a reason why, okay, I'm depicting here as a dashed line, okay, instead of the solid lines that we saw previously with the covalent bond. These are absolutely weaker than ionic bonds and covalent bonds, but okay, collectively, because when working together, you can generally be stronger and get more done. Collectively, as we're going to see, they can be quite strong if you have a lot of them working together.
So just to kind of visualize that, just so, and please correct my visualization if that's wrong. The first, to try to break the intramolecular, trying to make the water, the oxygen and the hydrogen, just not oxygen and hydrogen can connect anymore. Whereas enter would be splashing water and getting the different droplets to go in different areas.
Yeah,
and breaking up what used to be a puddle to go sklinkle.
Yeah, or boiling water of like liquid into steam.
Uh,
That absolutely,
uh,
and that we're gonna cover that. Or like
Freezing water.
in intermolecular forces are absolutely at play. There's a reason why. Okay, one of the special properties of water is the solid form of water, ice, floats on the liquid form. We don't actually see that very often of like the solid form of something floats on the liquid form of the same thing. Typically, the solid form of whatever an element or substance typically tends to sink in the liquid form of the same thing. But water is different. And that is driven, as we'll see, that's driven by the intermolecular forces. Pretty much, the intermolecular forces play a large part in giving all these special properties to water.
So would that be things like gravity and those types of things? Would those be considered that, or is that different?
That is definitely totally different type of
Okay,
force, but
okay,
absolutely
okay.
a good question to clarify. Although obviously the atoms and the water molecules they're still affected by gravity because everything on Earth is affected by gravity.
Yeah,
But like
because
yeah,
like in my brain, I'm just thinking like the like gravity and shit's the thing that keeps the water in the bucket down instead of floating up, but that's not really what we're talking about.
yeah, it's not holding the droplets together, so to speak.
Okay, okay, okay.
So what are intermolecular forces and like what's going on with these intermolecular forces? Okay, so as mentioned, okay, there's a number of different intermolecular forces. Okay, and these are between separate molecules. Okay, and we're going to try and go systematically, where I'm listing here some of the relevant intermolecular forces. Okay, and we're going to go through some of them. Some of them are more important than other ones, as in hydrogen bonds. Okay, we're going to cover it. I'm just giving you a preview. Okay, I don't expect you to understand everything that we're talking about here now. But just as a preview, hydrogen bonds, which we're going to explain, these are very important when it comes to biology and biochemistry, and well, pretty much just about everything when it comes to life on Earth. And the dipole, and the van der Waals. Okay, but pretty much the main message here, okay, is individually, again, intermolecular forces are fairly weak, but collectively they can be quite strong. Okay, and what I'm showing here, is well, carbon dioxide. Okay, CO2. It's a gas. It's that's what we exhale into the atmosphere. That's what plants use from the atmosphere to make all the stuff that plants make. But what ultimately what I want you, the take-home message that I want you to extract from this figure is this symbol here. Okay, this Greek letter delta. So we saw when we were looking at sodium and chloride, okay, we saw full positive charges and we saw full negative charges, as in sodium, full positive charge, chlorine, full negative charge. But here, these are partial charges, as in this delta here, these are partial negative, partial positive, okay? And what I'm highlighting here is the partial negatives, they're on the oxygen atoms, okay? The partial positive, that's on the carbon atom, and that's not a coincidence, and we'll get into the reasons why that is. So why is it here that carbon has a partial positive charge and oxygen has a partial negative charge, okay? So what's going on here? What's generating these partial charges? So what is generating these partial charges is this concept of electronegativity, okay? Now, what is electronegativity? So we covered covalent bonds. Covalent bonds, that's a sharing of electrons, right? Covalent. But the sharing is not equal. Obviously, it's not always equal. Some atoms can be kind of greedy with electrons, and that's what happens here. Where a covalent bond, okay, is a sharing of electrons, but the sharing is not always equal. So there are specific atoms that I'm highlighting here that are greedy with electrons, as in even though they form a covalent bond, okay, they're kind of like pulling the electron, saying, hey, spend more time with me. And that's effectively what happens with these molecules here, the carbon dioxide and the water molecule, okay? Where fluorine, oxygen, and nitrogen specifically, okay, those are very electronegative. And what that means is they're very greedy with electrons, as in a covalent bond, okay, they will have this tendency to, like, even though they're in a covalent bond, they're going to, try to pull the electrons toward them. They're trying to game the system, so to speak, a little bit.
Yeah, greasy.
Exactly. So, since oxygen is very electronegative, okay, and carbon's not very electronegative. It's essentially considered, not electronegative. So what happens is you have a covalent bond happening here, as in carbon in the middle, and it's maybe not obvious, but it's a double bond here with the oxygens, okay? As in C double bond O, and then C double bond O. That's why there's, two lines there, or two bars there of black and red. Because if you count up all the bonds, how many are there in total?
4.
Exactly, and as mentioned, carbon likes to make 4 covalent bonds. But if I asked you how many covalent bonds does each individual oxygen atom have, what would you say?
Well, if I recall correctly, did it not like 3 or something like that?
Close.
Or does it
Two.
2. Oh, okay. It only wanted 2. Okay, so those are
Exa-
just single ones on the hydrogens.
Yeah, exactly.
oxygen.
Exactly.
Yeah,
so
okay,
that's why if you look at carbon dioxide, okay, if you look at each individual oxygen, it's forming a double bond with the carbon, as in oxygen number 1, double bond with the carbon. So, and then oxygen number 2, double bond with the carbon. So carbon gets the 4.
Yeah, and
bonds.
hydrogen couldn't have a McDouble because then that would make it have 4 electrons. And it can't do that.
It would have, it'd have too many electrons basically at that point.
Yeah, it doesn't like that.
So these are it's a nice demonstration of the rules at play. Of carbon has 4 covalent bonds. Each oxygen, okay, everyone here has 2 covalent bonds. Of the oxygen, the water molecule, it just has one bond with one hydrogen and another bond with another hydrogen. So what's happening here in each scenario, okay, is since oxygen is greedy with electrons, okay, it starts, pulling electrons away, in this case, from the carbon. It's not extracting them, okay? Let me be clear. It's not extracting electrons, it's not transferring, it's just like,
Sucking a little more power from them.
Exactly right. Pretty much, just like trying to lure them away, but they're not actually like fully going their way. That's what's happening in each scenario. And so that's why, since the electrons from the carbon are spending more time with the oxygens, okay, you get these partial negative charges on the oxygens, okay? And same thing's happening with the water molecule. Since the oxygen, okay, is way more electronegative than hydrogen, hydrogen is considered not electronegative. It pretty much has no power to pull electrons towards. It's basically the loser when it comes to electronegativity. And so that's why you get this partial negative charge on the oxygen, and you get partial positive charges on the hydrogens and the carbons, since they're basically, their electrons are being lured away a little bit, okay? And this phenomenon, okay, with the dashed lines, we call them dipoles, okay? Where we call it a dipole because, well, there's a pole to it of a partial negative charge and a partial positive charge, and it's between 2 atoms, hence the dipole. Just as a magnet has a north and south, that you can also consider that sort of a dipole. Like you have 2 poles of a magnet, a dipole, a north and a south. You have 2 poles here, a partial negative and a partial positive. You have a dipole between those 2 atoms.
And that's not like an additional like bondy thing. It's just kind of like a way of showing and explaining that negative charge.
Exactly.
It's not like there's an additional bond. Okay, that makes sense.
Exactly.
And what happens if like a fluorine and an oxygen fucking get going together? Like, and they're just both greedy fucks. Do they just like have a bad time and they're unstable, yelling at each other, just like fuck you, dude?
Well, in that case, although fluorine and oxygen will not have a tendency to interact with each other, but even if they do, if you cram them in a cage, fluorine will win. Pretty much because fluorine is the most electronegative. Fluorine is.
There it is, right there.
Fluorine is the king or queen when it comes to electronegativity.
Just the succubus of fucking, like, the most succubus of all the atoms.
In a tug of war of electrons, okay, unless it's between 2 fluorines, fluorine is always going to win out in the competition.
So what happens there?
Yeah. So what happens there is it's you. That's why I use the metaphor of a tug of war. Like if you have two people of equal strength in a tug of war tugging, what
Well,
happens?
yeah, it's so is that gonna be super strong? Or does it get
Uh,
weak over time like a tug of war where they're just like, oh my God, why are we even tugging anymore? Let's just stop. And then they
well,
just
yeah.
like
In
give
that
up
in
and go
that
their own
case, you
way.
you will not generate a dipole, as in you will have no
Mm.
partial negative, you have no partial positive. No one wins in the tug of war. Basically,
Uh,
to generate a dipole, you have to have a winner.
okay. Yeah, 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 yeah. Okay, that makes
One
sense.
has to be stronger.
Okay,
So,
cool.
and I think this should be probably the last slide because I want to respect your time.
Good.
But
Fucking
just, and I think this is a good place to
trample on
like.
my time. I'm having a good time. Let's go.
So, how do these dipoles and partial positives? So, okay, how do what's the relevance? Who cares? How does this affect how molecules interact? Well, as I highlight, okay, it actually matters a lot. Why does it matter?
Mm.
Okay, I use water as an example a lot because, well, it's relevant in biology and biochemistry. So now let's say you start with, your singular, okay, water molecule. But, do you ever really encounter like one single water molecule in nature? No. Pretty much, if we had the ability to just like single out one single water molecule, that would be pretty powerful. But like we don't ever encounter nature just like one lone water molecule sitting alone in nature. We have lots of water molecules. So as a result of the dipole in water, it can interact with itself. What do
Oh
I
shit.
what do I mean by that? Well, what if now you have two water molecules and,
Oh no.
in your glass of water, okay, they're going to be randomly oriented, moving around, floating around, okay? So you're not going to have like, just one or two. You're going to have lots. Obviously, I'm not going to, I can't fit trillions and trillions and trillions on this
What
slide.
the fuck? Come on. At least 1 trillion. You don't need trillions.
I
Just
know,
one.
well, I'm a
A
lazy
singular
person.
trillion. Like, come on, a billion at least.
But
Put some
yeah,
work
so
in,
now
Finn.
let's say you have a bunch of water molecules, okay?
Oh
So what ends
shit.
up happening, okay, all of these water molecules, I put them there. You have partial negative charges and you have partial positive charges. And so they're semi-randomly oriented. So let's say now you have this random water molecule, okay, oriented like this, and you have this water molecule here oriented like this. Well, okay, they happen to be, okay, just
Oh
nicely
shit.
oriented that the partial positive and the partial negative can interact. Okay, and
Do they
this
have to be? I know this may be a dumb question, but does it need to be like, yo, this one's like a point 0.6 positive and this one's like a point 0.4 negative, and they just like kind of
there,
like
there
go
I-
like, I guess that wouldn't really work. Or like a
no, no,
-6 or +6, and they just go
uh,
bling bling, or does it
no,
not
no,
really
you're right.
matter?
So there is a threshold, but like pretty much like what happens in water like totally like far exceeds the threshold. Like
Okay.
yeah, like pretty much there's no issues about that when it comes to water. You will always have pretty much this phenomenon occurring in liquid water.
Yeah. Okay. Cool.
And so, since you have, each individual water molecule has partial positive charges and partial negative charges, okay, well, they can opposites attract, okay?
Yeah.
These are not full opposites, but they're partial opposites, okay? So, you start adding them up and
Oh shit.
you start getting, okay, intermolecular force after intermolecular force, okay? Where they can form this network, okay, of intermolecular forces, okay? And one way to classify them, we can call them dipole-dipole interactions, okay? Because as we mentioned, okay, there's a dipole there in each water molecule between the partial positive and partial negative charge. So it's like dipole number 1 interacting with dipole number 2, and you have this, dipole-dipole interaction. Okay, and that happens pretty much all throughout. And if you extrapolate it to, trillions and trillions of water molecules, you get trillions and trillions of intermolecular forces.
And so, just so that I understand, because I think I might answer my question with this question. So, they aren't perfectly like matching and canceling each other out. So, like,
No. Th-
the positive hydrogen in the middle left that's getting double teamed by the oxygen in the top or left and the bottom middle. like that one there is still positive. It's just like maybe not as, it's definitely not as positive as it would be if it wasn't getting double teamed by two negatives, because they're not exactly like canceling it out and making it like a neutral nothing.
No, yeah. This is essentially additive. That's why
Yeah.
that's why
Okay.
collectively they're strong, and that's why I highlighted here. And I'm gonna try and pose to you an example of like how this plays out. So
Yeah. Yeah.
I include this note of, I think most people know, like the boiling point. What's the boiling point of water? It's 100 degrees Celsius. Well, at like, you know, whatever standard temperature and pressure, you know, and standard like elevation. Where like, yeah, to get your water to boil, yeah, have to heat it up to 100 degrees Celsius. Okay. Now, if I asked you the question, okay, of let's say comparing it, okay, let's say to alcohol, drinking alcohol, okay.
Yeah.
Now, if you, let's say, take Everclear, okay, which is like 100%, from what I understand, 100% pure alcohol, or even like vodka, which is
Borderline.
like,
Yep.
yeah, which is like, I don't know, vodka's like 40%, 70%, I don't know, I'm so ignorant on drinking
Yeah.
alcohol.
Me too. But I think it's probably in the 40 range.
But so let's say, okay, let's say you heat up your vodka, okay, let's say you have a liter of vodka and you have a liter of water, okay, and you put them on the stove at, you know, the same heating temperature. Which one do you think will evaporate first?
The water.
You think as in, you think water will evaporate first if you compare it to alcohol?
Maybe not. Yeah, no, probably the alcohol, because like I'm going based off of freezing, because I know alcohol doesn't really freeze, but like
Uh,
water freezes.
yeah,
So I was thinking that like it was like the other like same thing where like it'd take a while for it to boil, but no, like also like I feel like it'd probably burn off pretty quick. Yeah,
uh,
it'll evaporate at room temp, is what Chad's saying, and I like agree with like my ISO. Like if I have my isopropyl, if I don't
yeah,
put the
you're
lid
rubbing
back
alcohol.
on,
Exactly,
it's like
exactly.
gone.
Exactly. That's what you
So
use.
yeah,
That's what typically used
it
to
would be the
disinfect
alcohol.
or you know, yeah, disinfect, you know, skin or wounds or whatnot. Rubbing alcohol. Of
Lungs.
like, yeah, if you put a drop of rubbing alcohol, you know, on your desk, and you put the same volume of water on your desk, like which one do you think will evaporate first?
Yeah, definitely the rubbing alcohol. That makes a lot of sense when you put it that way. Cause
Exa-
yeah, like honestly, you have a bottle of fucking like 90% ISO and you mark it, leave the top off, and then come back a few hours later and see where it's at, because it's going to be lower.
exactly. Where it's like you pretty much leave it overnight and it'll be all gone. And like, yeah,
Yeah, for real. I've
a
done
glass.
that.
A
That's
glass of
pissed.
water like will eventually evaporate at room temperature, but it'll take much longer. Okay, probably like, you know, a day or two or something like that, as opposed to like, yeah, you're rubbing alcohol, and the reason for that, okay, the reason why, okay, you actually have to input in comparison. You have to input a lot of energy in the form of heat to get water to boil or to get water to evaporate. It's because of this network, this massive network. Again, you have to think of like trillions and trillions, you know, an insane amount of water molecules with all these intermolecular forces at play. And so you have to pretty much break up that huge network of interactions. That's why I say collectively, okay, the intermolecular forces can be quite strong. As opposed to, okay, your isopropyl alcohol or your drinking alcohol like vodka, okay? If you just like let it sit at room temperature, like given a few hours or maybe like overnight, it's going to evaporate like pretty quickly because it does not have the same ability, and we're going to cover a little bit. It cannot form the same network of these intermolecular forces. Alcohol can form intermolecular forces, but absolutely nowhere near to the same extent. And I use this example, okay, where you have formaldehyde, okay? Formaldehyde.
What is formaldehyde? Like,
Uh,
is that like what is that? Like, are you gonna die from breathing that? Like, that sounds like one of those if you breathe near it, you're gonna die things. Like chloroform.
Yeah, it's definitely like do not consume it, or pretty much like, yeah, if you can avoid it, or if you're going to handle it. Not that it's not like the most toxic thing in the world. Well, definitely like
Yeah.
never drink it, but like, yeah, we use this pretty routinely like in the lab.
Twitter's
But
the
like,
most
you know,
toxic thing in the world. So
yeah, that's true. But okay, the chemical formula, okay, of formaldehyde is just CH2O. So it's basically in terms of chemical formula, It's H2O with an added carbon. The
Pretty much
structure,
water.
in some sense, yeah, but the structure is like quite different. As in, so here's a nice example of like how many covalent bonds do you see that the oxygen has?
Ooh, there's a
Exactly.
McDouble on that bad boy. Yeah,
And how many covalent bonds do you see that the carbon has?
4.
Exactly. And the hydrogens, they only have one. So that
Yeah.
fulfills the rules of carbon likes 4 covalent bonds, oxygen likes 2, and hydrogen likes 1. So
Hmm.
now, okay, even though the chemical formula for formaldehyde is quite similar, okay, the boiling point to get this to boil, it's minus 19 degrees Celsius, as in like this will pretty much like almost instantaneously like evaporate, because, and that's driven by the fact that formaldehyde, okay, it cannot form the same intricate network of bonding or intermolecular forces that occurs here in water. And so that's why water has this pretty unique property of like, yeah, this network of intermolecular
Uh,
forces and its ability to interact with itself and interact with itself a lot,
uh,
and in unique ways that we're going to see. Where you brought up like the freezing of water, and like again, ice has some pretty unique properties in terms of, you know, ice floats on water, and that's pretty special when it comes to, again, a particular substance, the solid substance floating on the liquid substance of the same thing. So
uh.
yeah, I think this is a good place to stop, since I think I'm bombarded you with a bunch of
No,
information.
that's fucking super interesting. And once again, the reason why fucking formaldehyde can't do that shit, it doesn't get that dipole shit because fucking carbon isn't as fucking like greedy as fuck as that goddamn landlord oxygen who just wants to suck up all your fucking power from your electrons. And that
Exactly.
fucking carbon is a comrade and kind of cock blocks it.
Yeah, exactly. As in terms of
And that
the
and well,
dipole is
yeah, the dipole party.
exactly. The dipole party is totally different here. It's not nowhere near as sophisticated as what you observe in water, because you just can't form this type of thing with formaldehyde. Because yeah, the
Yeah.
dipole is totally different. We're gonna see examples more and more. We'll reinforce this concept as we
Hell
go,
yeah.
and it'll
Reinforce
become.
me.
Oh yeah, I'll definitely do that as much as I
Let's
can.
go.
So yeah, you know, I think this is a good place to stop. They went to actually even a little longer than I anticipated, so I
Oh fuck,
apologize.
get used to it. Oh fuck no. Fucking fucking there's no way we're gonna be able to do this in an hour. This has been fucking sick as fuck. And I look forward to it. I feel like I've already learned so many cool things about things.
And well,
Fucking that's sick.
maybe just as a preview, because I thought we would get to it this time, okay? But someone asked the question about, you know, what is life? I don't know if they're still around, okay? But
Ah
uh,
yes.
okay, I included that slide. Okay, the next section is biology basics. We're wrapping up the chemistry basics. We'll do it next time. But like, yeah, there's no universally accepted definition of life. Okay, we pretty much go with the cell is the fundamental unit of life. Okay, life is more of a property and a characteristic as opposed to like this is our definition. It's hard to define. So it's a great question. We'll try to address it further next time. Next time we'll definitely get into the biology basics, and we'll wrap up
Oh
the
yeah.
chemistry basics. We're almost done the chemistry stuff, and then the biology basics is I don't think it's super long, and then we're gonna start doing our
Oh,
deep
that
dive.
shit's gonna get so gnarly, dog. Holy shit, dude. I am so stoked. Hell yeah. How you said one more chemistry and then bio?
Yeah, I think there's without giving because well, I've
Yeah.
prepared questions. I'm making sure that I'm avoiding the question slides.
Ooh, shit.
Where we're here. So yeah, there's about let's see. Yeah, there's actually about 3 more slides left of chemistry basics, and
Oh
then we get
fuck
into
yeah.
biology.
Hell yeah. I'm stoked about like the test questions and shit too. Fucking cause I wanna know if I fucking get the thing and understand the thing. But I think I'm fucking getting the thing and understanding the thing.
Yeah, I absolutely have no doubt that you are, especially like based off of your questions. And your chat is asking really good questions. That question about life is like super great. I'm glad that they asked it. And yeah, like this has been, at least for me, this has been fantastic. and I super appreciate you agreeing to do it. And I super appreciate your attention and all the great questions that you asked. And I guess I should ask you, do you have any other outstanding questions or comments, feedback,
Um,
or yeah?
Yeah, no, I'm super fucking stoked for the next one. And learning more. Fucking this has been fucking super awesome. Yeah, my only feedback is like don't fucking be concerned about my time too much. I appreciate it. But fucking if you need more time, I'm good on that cuz like this shit's fascinating and I'm learning a bunch.
I'm super
Oh,
glad to
thank
hear it.
you.
That's what matters to me the most. In terms, one is like, yeah, is it at least interesting enough? I try my best to make it interesting and engaging. I can't promise it. I'm trying to incorporate,
Been great.
relevant stuff, and as we go, we're gonna cover research and try to bring in the research and what I think are cool things. But right now, I would say like, this is the in my mind, this is like the driest stuff of like, yeah, laying the foundation for the chemistry stuff, the biology stuff. But then I think once we get into the biochemistry stuff, okay, hopefully, things take
Welcome
off
to
there.
Flavor Country.
But yeah, this has been great. I want to respect your time.
Awesome.
Yeah, I can't thank you enough for agreeing to it. Now, I also look forward to the next time. And like I said, okay, and if your chat like or even if your Discord has feedback of like, hey, Corey should make this change to like whatever the presentation or whatnot, I'll absolutely welcome it and take it into consideration.
Yeah, fuck yeah.
And like I said, my presentation is a living document. I'm going to be updating it as we go. We might be revisiting some slides of like, oh, I added to this. I don't know. I'm still like, this is a work in progress, basically.
Fucking absolutely amazing. Well, if this is a work in progress, I'm loving the progress you're making. Fucking this has been fucking so awesome, dude. Thank you so much. I really enjoyed this and I look forward to doing more. Because this has been fucking sick as shit, dude. I've
I
learned a
feel the
lot.
exact same way. And yeah, I can't thank you enough. And yeah, well then we'll absolutely be in touch. And well, I'll see you around in the Discord, and I'll see you around in your Twitch chat and all that stuff. And thank you so much
Absolutely.
for being my student, basically.
Absolutely. Much love. Thank you. Have a
All
good
right,
one, my dude.
take care. Be well.
Bye. Thank you. You too.
All right. I missed a bunch of follows, which so welcome Time Scroll. Much appreciated. Think you mentioned something about you being a chemist. Yeah.
Welcome to Flavor Country.
Thank you for the follow, Fafresh. Much appreciated. Happy to have you here. And thank you so much for the kind words. I try to make it cool. I'm gonna try. Okay, again, this is a work in progress. I'm gonna try and make it even more cool. Can't make any promises. But like, yeah, I did actually invest quite a bit of time in like making the presentation and all that stuff. But I'm still learning the ropes of Canva and all that stuff. Where I think I can probably do it even better. Oh yeah, the casual. So I am not stopping that. I'm still going to be reviewing biochemistry papers, absolutely. Just give me a second. I'm probably going to change my view. I want to close this. So pretty much, okay. I should be back to making content because like, hopefully you can see that I've prepared content. I have like a full presentation that I'm constantly working on to present week to week. And actually, I think, let me just double check. Because, so as of right now, I prepared about 50 slides, okay? Or no, 55, 56. With the sort of like, I had what I was thinking in my mind of like, well, an hour we'll probably get through like 20 slides or so, or pretty much I thought we'd get through like half of the 55 slides or so that I prepared, but I was incorrect, as in I might have given myself even more time to work on it from week to week. because we got to slide, which I don't say this as a complaint. I actually more say this as a good thing in terms of I over prepared as opposed to under prepared. Of like, if we're going at this pace, which this is a pace that I like, of like time to explain things, time to provide more detail, take questions. We got to like slide like 16 out of 55. So, you know, if we're going at that pace, then, you know, as of right now, I have 3 weeks worth of slides to work with. But again, I'm going to be adding as I go. So this went better than I anticipated. So let me just close this. 1 second. Okay. But yeah, thank you everyone for tuning. Thank you for the follows. I have a bunch of follows to thank. 1 second. Fall Fresh, thank you for the follow. Energy Flow, Justin Freakin, thank you so much. I believe I've seen you around, I think, in Prime's chat, maybe. The Sacrificial MILF, super cool username, much appreciated. Thank you for the follow. Venus Bloodflow, also a cool name. Biochemistry related for sure. So yeah, that was great. So yeah, I should be back to making content regularly. And pretty much my original plan is like, yeah, obviously my original plan is like, week to week, okay, covering the biochemistry, or at least building up to starting the biochemistry. Right now we're in the introductory phase of, again, laying the foundation of chemistry, biology. And then we're going to get back to covering research, for sure. In terms of, I want to get back to covering research papers because I have a giant backlog of research papers that I need to get through, or that I want to start covering, because there's always interesting research, being published. So as of right now, my tentative schedule, I pretty much have committed myself. I've blocked off Wednesdays. Like, this should be this time next Wednesday that we come back to the biochemistry lecture. And then I think Wednesdays and Sundays should be my streaming days, where basically Wednesday biochemistry, and maybe if there's time left, some science and news, and then Sunday covering my usual research papers and all that stuff. And also, as I mentioned in the Discord, and feel free to join the Discord, because I will be way more active there, providing updates, and I should be putting any research that I cover on stream, putting it in the Discord, although it seems like my stuff doesn't work in terms of my commands. Let's see, does this work? Nope, doesn't work. Not the end of the world. What I will do... Yes, that is the Discord link. Feel free to join. Because, like, yeah, I should be back to making content because I've committed to this project. And as I mentioned in the Discord, I've written a Substack, at least so far one outlining pretty much my entire experience, okay, with the company that fired me back in November, December. They fired me after 5 days. And as I mentioned when I briefly covered it on stream, of like, I recorded the audio of a meeting. I legally recorded the audio of a meeting. And in my Substack write-up, giving all the details of my entire experience from day 1 to day 5 and my firing, and the final meeting with pretty much the team. So probably going to read that on stream. And then I plan to write up other Substacks, where I have a bunch of ideas for Substacks that I want to write. and I'll probably use that as content as well on stream. Probably at some point, but I'm not the quickest writer. I'm probably not the best writer either. So, you know, I tend to spend a lot of time like editing and proofreading and all that stuff. Where the Substack, detailing my experience with the company that fired me, you know, that's in the proofreading editing stage. Although it's been like that for quite a while. I think it is essentially done. I just need to, you know, whatever, commit to pressing publish. But, you know, I just have this tendency to proofread. Same thing with the presentation that I just went through, part of it, of like, I must have gone through that, you know, 20, 30 times, like making sure all the animations are correct, you know, making sure that it's hopefully aesthetically pleasing and the figures make sense, and whatever, the graphics are at least somewhat aesthetically pleasing. You know, I probably spend too much time in terms of like, whatever, preparing things and like editing things and all that stuff. But regardless, I am glad that I'm back to making content. It's been too long, and thank you for everyone being patient with me. Thank you for everyone for passing by. Time scroll, super appreciated. I will be back to covering research papers. Thank you, Justin Freakin, for the follow and passing by. And if you're a nerd, then you will fit right in because I am a giant nerd. Kitty the Pet, thank you so much for passing by. Always a pleasure. I think pretty much like one of my first follows ever. I think even before I was at 100, less than 100 followers, you were a follower. And Smash, thank you so much for passing by. Great to see you. Hope you're doing well. The one Real Greenman, and Bob Marley. Can't forget you. Also, pretty much one of my most loyal followers. Can't thank you enough for everyone for being patient in my return. So, that's pretty much all I had prepared for today. It took longer to get everything up and running in terms of like the presentation and ironing out some of the kinks with whatever, getting the Discord set up, getting the stream layout properly. I'm probably going to save this for, let's say, Sunday. Oh, Wildcat Antifa Demon, welcome. Thank you so much for passing by. Venus Bloodflow. Thank you for the raid, I believe. I think my notifications. My notifications are Globus. I don't think my shoutouts are working. One second. Yeah, I gotta turn on all my commands. Although, no, there's still the Twitch shoutout. Apologies, my stream game is a little off because I haven't streamed in a while. But great to see you, Globus. Hope you're doing well. I totally lurk in your streams when I can. Covering the AI stuff. Always great, and thank you so much for all the research that you send me in regards to AI and biochemistry as well. And thank you, Venus Bloodflow, for the follow. Super appreciated and happy to have you here. And well, thank you for the kind words. I did my best. As I tried to emphasize, my presentation is a living document. I will be amending it, hopefully improving it as we go. You know, this is all sort of in the prototype or preliminary stage. I'm hoping to get an overlay made at some point that, you know, looks like a classroom, that, you know, I can have, Tyler's, you know, picture or cam there and my cam there, sort of like, in the setting of a classroom. And maybe, hopefully, ideally, I can maybe, invest in a green screen, where I can have, like, my full background as, like, the presentation, as opposed to just, like, you know, a window. I understand if maybe my background, my moving background is a little bit distracting. Oh, well, thank you. I appreciate that. I do my best. I do enjoy teaching. But unfortunately, I didn't have much more content than that prepared, since I was so focused on getting the presentation right that I didn't prepare anything else. Yeah, you mentioned the Video Ninja. For sure. I've looked into it. It looks interesting. I haven't tested it out, but you know these things better than I do. So if you think that's better and to use that, we will totally use that. And again, fingers crossed. I'm pretty sure I should be able to invest in a decent green screen pretty soon, where I can have my entire background as like, you know, whatever, the screen, as opposed to just like a window. That hopefully improves the experience. But yeah, thank you so much for the raid, and I can't thank you enough, Tyler, for agreeing to be my student. And yeah, I don't think I could like picked or have thought of a better person that I would have wanted to, you know, present this stuff to and collaborate with, because like, yeah, you were absolutely asking, and your chat were asking fantastic questions, and also you make it interesting and entertaining. Yeah, I totally agree with you that a little bit bigger would be great, and I am absolutely working on it. So I will absolutely take this feedback. Any feedback is appreciated. I can't guarantee that I'll incorporate it, but I'll absolutely do my best. I'm always open to feedback and criticism. But unfortunately, I think we'll have to hopefully pass on the friendly raid to someone else because I didn't have any other content prepared. But I should be back to streaming now regularly. Now that I have this project to work on, and you know, I know the content that I want to cover. You know, I have a whole textbook now that I want to cover, so that should cover me for a while. And getting back to my usual research streams and covering research papers that are interesting. But we are going to pass along the raid to someone else. Oh well, Squidadair is streaming. Let's see, there's also, who else? I think Squidadair is a good person to raid. Yeah, I will absolutely set that up. Well, thank you. I look forward to it as well. Now, that's why when I was thinking of this project, okay, Tyler was absolutely, like, pretty much the only person that came to mind of, like, who would I want to teach this to and collaborate with to do it. And that's why I'm super happy, and I'm also looking forward to it. And again, making it better, hopefully making it more entertaining. Let's see. Oh, I see that Twitch has changed the way that you raid someone. I'm totally out of practice. Okay. Yeah, it looks like Squidadair is streaming, and we can raid them. So I'm gonna start the raid. So yeah, thank you everyone for passing by. Thank you for attending, paying attention, and returning to my stream after a 3-month break. Thank you everyone. Wildcat, Venus Bloodflow, Tyler, Bob Marley, Globus, thank you. Anybody else that I forgot, I apologize. Time scroll. And we are going to raid into Squidadair. Gonna set that up. If you're not following, I'm pretty sure everyone in Tyler's stream knows Squidadair. But if you don't, you should definitely be following them. And yeah, I should be back Sunday. If not, Wednesday, since again, that's what I blocked off for our biochemistry lectures with Tyler. And yes, until next time, take care and be well, and give a follow to Squidadair.
Unless that guy has a special emergency.